Hello, everyone. This is Lisa Schaefer. Welcome to Module 3 of the Fall 2024 Stormwater Management Design Review course. The time is 1:04. We have started the recording and we're going to start at 1:05. Now, for now, your microphone and your camera are off. So if you can, please use the chat. One last time, if you are watching as a group, we need to know who is present with you. If you're by yourself, most of you, your username shows your full name, so we can identify you from the attendance data. However, there's one or two other people who haven't already identified themselves and are showing up as a title, and we need to know who you are to give you credit. So I appreciate your taking this time to let us know. Use the chat if you can. Otherwise, use the DWQ email account. All right, and so now it is time to start. And as I said, my name is Lisa Schaefer. We have Module 3 today of the Stormwater Management Design Review course. So we have a very tight schedule today. So to better address your questions, just please use the chat. Staff will get to them as soon as they can. I see there's one for me about attendance. I'll take care of that in just a moment. But don't forget, you can also email your questions now. And if we run out of time to answer your questions verbally after each presentation, we will try and get to them at the end of the day as long as we don't run out of time. So that being said, we're going to get started. And today we will begin with a review from quiz number 2, which you took on Thursday. So please stand by while Peter takes control.
All right, well, good afternoon, everyone. Welcome to the third module of the course. My name is Peter Plantos. So as Lisa said, we will be starting Module 3 with the Quiz 2 review. After the quiz review, we will continue Module 3 as scheduled and outlined in the handouts provided. All right, so let's begin the review. The first 3 questions on the quiz were general information type questions. So we will begin here at question number 4. True or false? There is no longer a minimum or default value that can be used for time of concentration using the NRCS methodology, meaning this value must always be calculated. And that is true. There is no longer a minimum or default value that may be used for the time of concentration. Time of concentration, or T sub C, for pre- and post-construction conditions must be calculated based on the flow path. All right, question 5. According to the NJ Stormwater BMP manual, what is the maximum roughness coefficient that can be used in sheet flow calculations for wooded conditions in New Jersey? And the correct answer is 0.4. The maximum roughness coefficient that can be used for wooded conditions is 0.4. Though the National Engineering Handbook lists Manning's roughness coefficients as high as 0.8 for woods with dense underbrush, for New Jersey, the maximum roughness coefficient for sheet flow that may be used is 0.4. New Jersey does not contain land cover that supports the use of roughness coefficients associated with woods with dense underbrush. All right, number 6. What is the maximum sheet flow length for the pre-construction condition, assuming there is no physical constraint present to prevent sheet flow from occurring? And the answer is 100 feet. For the pre-construction condition, the maximum distance for which we can assume sheet flow occurs is 100 feet, unless there is something physically in contact with the flow of stormwater runoff, such as a swale, curb, or inlet, to prevent sheet flow from occurring. Remember to use the actual distance if it's less than 100 feet. So this comes from Chapter 5 of the BMP manual if you have not taken a look at that yet. And again, remember to use the actual distance if it's going to be less than 100 feet. Question 7. According to the Stormwater Management Rules effective on July 17, 2023, which methodology can be used in the computation of stormwater runoff? And the correct answer is the NRCS method. The Stormwater Management Rules effective on July 17, 2023, removed the rational method and modified rational method from NJAC 7:8 5.7 and only allows the NRCS method to be used in stormwater computation. Number 8, true or false? When using the NRCS methodology for directly connected impervious cover, averaging pervious and impervious curve numbers is permitted for calculating a hydrograph. This statement is false. Here's a quote from NJAC 7:8 5.7A4. In computing stormwater runoff from all design storms, the design engineer shall consider the relative stormwater runoff rates and/or volumes of pervious and impervious surfaces separately to accurately compute the rates and volume of stormwater runoff from the site. This statement does not apply when using the NRCS composite curve number with unconnected impervious area method. See Chapter 5 of the BMP manual for more information. Question 9. When determining the curve numbers for site design, the design engineer should assume that the condition of the existing cover is good condition is the correct answer. This is fairly straightforward. Pre-construction condition curve numbers should assume that vegetated areas are in good condition. Question 10, yes or no? Can the Delmarva dimensionless unit hydrograph be used for the redevelopment of a 2-acre entirely impervious site located within the coastal plain? The answer to this is no. The Delmarva dimensionless unit hydrograph must be used when modeling watersheds within the coastal plain region of New Jersey, with just a few exceptions. It cannot be used to size a manufactured treatment device, or MTD, as it may underestimate the peak flow rate entering the MTD. Also, for an entirely paved site, the significant surface storage associated with the coastal plain is no longer present, also resulting in underestimated peak flow rates if the Delmarva is used. Additionally, the Delmarva should only be used in areas that have an average watershed slope less than 5%. If any of these situations are proven to be present, the SES standard dimensionless unit hydrograph must be used. And a side note on this subject, if the Delmarva is used in the pre-construction condition, it must also be used in the post-construction condition. Same idea goes for the SES. Number 11, true or false? When using the NRCS methodology for calculation of stormwater runoff, the Type 3 rainfall distribution must be used for developments in New Jersey. The answer is false. As we went over in the calculations presentation, NOAA C or D distributions must be used, not the Type 3. Question 12, true or false? Pretreatment must be incorporated into the design of a small-scale GIBMP that has a drainage area greater than 1 acre, infiltrates runoff into the subsoil, and uses exfiltration in the routing calculations. This statement is true. All small-scale GIBMPs which are designed to infiltrate into the subsoil and have contributory drainage areas greater than 1 acre must include pretreatment of stormwater runoff when using exfiltration in the routing calculations. Question 13. Soil testing logs prepared in accordance with Chapter 12 are required for which of the following BMPs? And the correct answer is all of the above. They all have a minimum separation from the seasonal high water table, which you can find in their respective BMP manual chapter. Soil testing would therefore be required for all of these to ensure that they meet the required separation. Question 14, true or false? A factor of safety of 2 must be applied to the slowest tested saturated soil hydraulic conductivity rate to determine the design saturated soil hydraulic conductivity rate, which is used for infiltration BMP calculations. This is true. Since the actual saturated soil hydraulic conductivity rate may vary from soil testing results and may decrease over time, a factor of safety of 2 must be applied to the slowest tested saturated soil hydraulic conductivity rate to determine the design saturated soil hydraulic conductivity rate. Computing a BMP's drain time for the maximum design volume, the exfiltration rate for a BMP allowing exfiltration in the routing calculation, or the infiltration rate in the groundwater mounting analysis must all use the design saturated soil hydraulic conductivity rate. Number 15, yes or no? During the month of July, can the seasonal high water table be determined by measuring water levels directly within a soil exploration if the modeling does not indicate redoxymorphic features are present within the soil exploration? And the answer to this is no. If modeling does not indicate redoxymorphic features are present within the soil exploration, the seasonal high water table may be determined via direct observation of water levels only between January and April. For more information on determining the seasonal high water table, see subsection 1D of Chapter 12 of the BMP Manual. Question 16. When is it necessary for the design engineer to assess the hydraulic impact on the groundwater table? And the answer is whenever an infiltration BMP is proposed. You should assess the hydraulic impact on the groundwater table anytime an infiltration BMP is proposed. This would include any potential drainage issues and potential damage to nearby structures. Question 17. How many soil profile pits and/or soil borings must be performed for 5 small-scale bioretention basins in one mapping unit that are each 450 square feet and scattered around a development? And the answer is C, 1 soil profile pit for the soil mapping unit and 1 soil boring for each small-scale bioretention basin. So we know from Lisa's soil testing presentation that if an infiltration BMP has an infiltration area that is less than or equal to 500 square feet, you would have to do a minimum of 1 soil profile pit per soil mapping unit. You would also have to do 1 soil boring per BMP as well. If the BMPs are going to be located in different soil mapping units, each unit must have 1 soil profile pit. But if you read the question here, the 5 basins are going to be in 1 mapping unit. So in total, 1 soil profile pit for the 1 mapping unit in this example, and 1 soil boring per small-scale bioretention basin. Question 18, true or false? In a small-scale infiltration basin, the 2-foot separation from the seasonal high water table should be measured from the surface of the sand layer. This statement is false. As stated in the BMP manual, for any designed infiltrating BMP, the separation from the seasonal high water table needs to be measured from the bottom of the sand layer, which is the lowest excavated elevation in the BMP. We mentioned the seasonal high water table separation requirement when we talked about why soil testing is so important. Question 19. Where on the soil horizon should soil permeability tests be performed when no soil replacement is proposed? And the answer to this is A. Soil permeability tests must be performed on the most hydraulically restrictive soil layer below the BMP and above the seasonal high water table or bedrock, to the greater of 8 feet below the lowest point of the basin, or 2 times the maximum potential water depth, as the permeability of this layer will be the limiting factor in infiltration rates. And question 20, true or false? When choosing a hydrodynamic separator type MTD, the inlet configuration, such as the angle and number of inflow pipes, must strictly match the inlet configuration described in the NJCAT verification report. And that is true. Manufacturers will try and offer other types of configurations, but this is not allowed. They must not deviate from the tested and certified configuration that the MTD was meant to be in, as they would not meet the certified TSS removal rate. All right, so that concludes the quiz review. We will continue Module 3 in just a moment. If you have any questions, feel free to type them into the chat or email us at the email shown on this slide. Up next is Manesh, who will go through the agenda for the rest of the module. Please stand by while I hand control over to Manesh. Thank you.
All right, thanks, Peter. Now let's get into the remaining agenda for Module 3. Today, we'll be tying into what was presented in the 2 prior modules and apply that information to reviewing projects. We will have how to review a project 1, which will be presented by Anthony Roblick along with myself. And we have how to review a project number 2, which will be presented by Chang-Yi Wu. After the how to review a project presentations, Peter will continue on with groundwater mounding, along with examples of performing the analysis that is required. And then we will have quiz number 3. And if we do have time remaining, we will briefly cover some of the common issues we have seen in designs. If not, though, we will provide those slides for reference. So let's get started. I, along with Anthony Roblick, who will take over in the second half of this presentation, are going to be going through part 1 of how to review a project. This presentation came about because our review of approved projects during compliance audits showed that projects were being approved, even though the calculations and stormwater management reports submitted for local approvals did not necessarily comply with the stormwater management rules and the local stormwater control ordinances. Therefore, should these projects fail, the municipalities involved would be in violation of their respective permits. So here are the goals of this presentation, which are by no coincidence the goals of a successful project review. We want reviewers to be able to identify the design and performance standards that must be met on site, review applications for compliance with green infrastructure, stormwater quantity, stormwater quality, groundwater recharge standards, and review BMPs for compliance with the design criteria in the BMP manual. The information required in the stormwater report is specified in the stormwater control ordinance, and checklists are available to help with the review. The reviewer must make sure that any information found missing from the report must be added before approval of the project. The checklist found at this link in the Tier A guidance document can help with your review of the report and help to just organize your observations and comments. Now we're going to look at what the reviewer needs to be looking for in the stormwater management report. The first step in the project review is to check if the application package is complete. All the items listed here must be part of the application. So pre and post-site and grading plans are essential, as are the associated calculations and any drainage area maps. The details in the report sections should match up with the information on all plan pages. Too often, we find that some parts or even all of the stormwater report do not match the site and grading plans because the report was copied from another project. So the reviewer must also be aware of whether or not the permittee has a more stringent standard of what must be in an application for approval. If so, the reviewer should be looking at all that information. The township's adopted ordinance, which should be posted online, is also a great starting place to find what information is required to be submitted. Another issue we see that should be checked right away is that the plans and reports should also be reflected in the maintenance plan so that the BMPs will continue to function as designed. Too often, we see maintenance plans submitted that were copied from other projects and do not match at all the project that was submitted. So, like I just said, it is important that the reviewer checks that the site description matches up with the plans. The drainage and discharge points all need to be checked along with any change in pervious or impervious coverage that includes regulated impervious surface and regulated motor vehicle surface for each subdrainage area. And then also soil information for the site should be included and be accurate. Lisa did cover this and the use of the web soil survey as a means for getting your soil information, and more guidance will be provided later on today. As a side note, print versions of county soil surveys are not always up to date and should not be used as your sole resource. The report must include the following information regarding design and performance standards when it comes to what's required, along with any applicable variances, waivers, or exemptions, and how the standards will be met. Again, we find that this is often missing or does not match up to what is on the plan. So this is very important that this information is provided. The reviewer must be sure that the following calculations are included in the report. Time of concentration, as discussed in Module 2 last Thursday by Anthony, is essential to characterizing a site. Time of concentration must be calculated and included in the report. Some permittees, they may require this information be submitted on a CD so that it can be checked. No matter the format, though, it is important to include all of this information, including storm routings, hydrographs, the groundwater recharge spreadsheet, a mounding analysis if it's applicable, and water quality calculations, and make sure it matches what's on the plans. So you saw this slide earlier in Module 1 in the overview presentation. Always check whether the project meets the definition of major development, because there could be a chance that it doesn't. Also be sure to also check the permittee's definition of major development, as it may be stricter than the department standard. To find that, the reviewer should check the permittee's ordinances. One note here, though, you need to distinguish the different types of surfaces, whether it be regulated motor vehicle surface, regulated impervious surface, or other types of pervious surfaces, and etc. in the report. There are one or more major development thresholds that may apply to the project that the reviewers should be aware of, including the residential site improvement standards, the permittee's stormwater control ordinance, and NJDEP land use regulations. As you see here, each has a definition that you need to pay attention to when you are doing a review. Once the reviewer has verified that the required information has been submitted and is accurate, they can begin to actually review the design and performance standards. The plans and report must address the information that's listed here. This information is crucial to determining whether the project was designed properly. Information such as whether the project is discharging to a flood hazard area or a Category 1 waterway are often not included, and therefore they're overlooked during the review. This information may also determine whether or not the project requires input from other agencies, such as NJDEP Land Use or even the Pinelands Commission. Under the current rules, a reviewer must ensure the proposed design complies with the design criteria established in the BMP manual, which in turn ensures the design meets the design and performance standards of the rules. If something is an alternative design or method of calculation, the department must be notified of the approval. Along with the other standards, reviewers must ensure the BMPs follow the green infrastructure standards. And for this, the BMP manual provides the design criteria and considerations for the individual types of GI BMPs. If the reviewer did allow for waivers or variances, they must be sure that they were applicable. Can waivers or variances even be granted? It's really not a straightforward answer, and to resolve this somewhat gray area, it's better defined in the new rules. So the amendments to 7:8-4.6 were made to clarify the conditions that would warrant the granting of a variance by a municipality for a major development project. The amendments are intended to ensure that municipalities are not granting variances under inappropriate circumstances. Municipalities do not have to grant variances, and they do not have to create a mitigation plan if they do not plan to grant variances. But if they do, they can create a mitigation plan that allows the evaluation of mitigation projects suggested by applicants, allowing for the consideration of projects that are submitted by applicants as is permitted at NJEC 7:8-4.6A3I. To eliminate any potential misconception that a variance is an exemption from attaining the stormwater management standards, the word exemption was removed from section 4.6 as part of the rule amendment. With the amended version of the rules, the ability to grant variances requires a little more effort by the applicant. Now, there must be a demonstration that it is technically impracticable to meet one or more of the design standards. The only allowable variances are for engineering, environmental, or safety reasons, and they all have to be spelled out very clearly. Cost is not really a factor here. The old low impact development checklist often included statements that something was not economically feasible, and yet cost information was not formally reviewed. Previously, there may have been a site-wide variance allowed, but now the rule located at 7:8-4.6 states a municipality's approval of a variance shall apply to an individual drainage area and design and performance standard and shall not apply to an entire site or project unless an applicant provides the required analysis for each drainage area within the site and each design and performance standard. There's a lot more to the mitigation requirements that must be met to obtain approval of a variance in the amended version of the rules. A mitigation must be part of the municipal stormwater management plan and follow these new requirements. It must be selected from the municipal list of mitigation projects, or it could be proposed by the applicant if it meets the criteria for the municipal mitigation plan. Must be approved no later than the preliminary or final site plan approval. It must be located in the same HUC 14. It must be constructed concurrently or prior to the major development. It must meet the green infrastructure standards. And the entity assuming the responsibility of maintenance for the project must submit a written agreement to the review agency. And lastly, the approved variance must now be submitted to the county review agency and DEP within 30 days of approval. Mitigation is required to receive a variance from the green infrastructure standards, but be aware that certain BMPs cannot be used as mitigation measures and that there are minimum sizing and drainage area limitations. Note that vegetative filter strips and grass swales are excluded as mitigation measures, and they don't address quantity control and groundwater recharge. Green infrastructure BMPs that are used for mitigation need to be sized to manage the water quality design storm at a minimum and are subject to the specified drainage area limitations. Variances from the other standards are as shown on this slide. Note that there is no waiver or variance allowed for groundwater mounding. That's because the steps listed in Chapter 13 of the BMP manual make it very clear that if the selected BMP fails to pass the groundwater mounding analysis, another BMP must be selected and assessed, meaning that a whole redesign will be required. The reviewer should also be able to determine whether linear development exemptions exist on the site. The following linear development exemptions may be granted if the requirements are met for each. And that is construction of an underground utility line if revegetated upon completion, construction of above ground utility line if existing conditions are maintained to the maximum extent practicable, and the construction of public pedestrian access if made of permeable materials and it is no longer greater than 14 feet wide. And finally, the reviewer may allow waivers to be granted for the enlargement of a road or railroad or to the construction or enlargement of a public pedestrian access if the requirements here are met. And they are as followed. Public need for a project that can't be met another way. Design and performance standards met to the maximum extent practical. Meeting the standards would require condemning existing in-use structures, and the applicant does not have and cannot get rights to other lands for mitigation. These specific exemptions were discussed earlier in Module 1. Water quantity is exempt if it's in a tidal flood hazard area and flooding will not increase. Water quality is exempt if the site has a NGIPD's permit with a specific effluent limit. And groundwater recharge is exempt for a previously developed area in an urban redevelopment area. It is important that the reviewer is aware of what urban redevelopment exemptions are and where they can be applied. Urban redevelopment exemptions can only be granted to previously developed areas of a site. The existence of woody vegetation is a telltale sign of whether this exemption can be granted. If the reviewer finds that woody vegetation has returned to areas of a previously developed site, the exemption is not going to be allowed. The reason being is that removing woody vegetation, putting new construction over this portion of the site will result in a loss of groundwater recharge. And then the reviewer can check the NJGeoWeb to determine whether the rest of this information is applicable to the site. So in summary, the following are the possible variances, exemptions, and waivers that may be applicable to the site. But it is important that the reviewer takes the time to make sure that they can be applied and that they are only applied to these specific portions of the site that meet these specific requirements. So moving on, the next thing the reviewer should be looking at is if the applicant is meeting the design and performance standards using green infrastructure. The rules require that the design and performance standards are to be met using green infrastructure. Like I said earlier, the rules do require this for groundwater recharge, stormwater runoff quantity control, and stormwater runoff quality. Subsection 5.2 of the rules includes 3 tables, and they list those BMPs that may be used to meet the design and performance standards. The tables found there specify information on how each BMP may be used. Table 5.1 coincides with Chapter 9 of our BMP manual, which are the green infrastructure BMPs, and they include cisterns, dry wells, grass swales, green roofs, GI MTDs, pervious paving systems, small-scale bioretention systems, small-scale infiltration basins, GI small-scale sand filters, and vegetative filter strips. Some of the BMPs cannot receive runoff from motor vehicle surfaces and therefore do not address water quality, and those are cisterns and green roofs. Others don't offset the discharge of stormwater runoff from the 2, 10, and 100-year design storms, so they cannot meet the quantity control requirement, and something like this would be like a dry well. A note here, not all MTDs are considered green infrastructure, but the ones that are considered are included here in Chapter 9. These MTDs have a vegetative or soil component that meet the GI definition. And lastly, these small-scale systems listed here have a limited drainage area that they can treat compared to other BMPs. As you can see, the column on the left includes the name of the BMP, and the column on the right includes the maximum contributory drainage area. So for example, if you are using a drywall, the maximum contributory drainage area is going to be 1 acre, MTDs 2.5 acres, and so on. Note, this is table 5.1. So again, we're only talking about MTDs that are approved for green infrastructure. In the past, we've seen projects that propose to design 2 small-scale green infrastructure BMPs that each have drainage areas just less than the maximum allowed contributory drainage area, side by side in the corner of the site, so as to try and get around the drainage limitation. However, a design like this is not going to meet the green infrastructure definition, because green infrastructure means a stormwater management measure that manages stormwater close to its source. The design of a small-scale green infrastructure BMP shall be distributed throughout the site and manage the runoff closer to the source that is generating the runoff. As you can see from the first diagram, the green infrastructure BMPs are all clustered together at the top. The second diagram shows 2 large-scale BMPs and proximity of each other. These BMPs would need to be spread out from each other to cover the entirety of the runoff of the site to meet the green infrastructure definition. Chapter 10 BMPs can be used to address stormwater runoff quantity control. These BMPs can have larger contributory drainage areas than the BMPs that are listed in Chapter 9. Chapter 10 BMPs include large-scale bioretention systems, large-scale infiltration basins, large-scale GI sand filters, standard constructed wetlands, and wet ponds that are GI. Note that though I said they can address quantity, these BMPs may only be used to meet water quality and recharge if a waiver or a variance is granted. BMPs in Chapter 11 are non-GI, and they always require a waiver or variance before they can be used. It's not really anticipated that these BMPs will be used much in the future because of what is required in order to grant a waiver or approve a variance. But as for some of the BMPs noted on this table, blue roofs don't have a reuse component, and extended detention basins are typically large and require additional treatment to meet water quality standards. The majority of manufactured treatment devices currently do not have a soil or vegetative component, so they fall onto this table. And then you see non-GI sand filters, subsurface gravel wetlands, and non-GI wet ponds to round out Chapter 11. The next thing the reviewer needs to look at is stormwater runoff quantity control. Water quantity impacts must be addressed to not only prevent increased flooding due to development, but also to avoid increased flow rates, which can significantly degrade water bodies downstream from a site. In Module 1, we cover the different options a designer can choose to follow. I'll briefly go through the options to meet water quantity control, as we have found this to be done incorrectly in many of our reviews. It is important to note that the reviewer must make sure that all points of discharge from the site must meet the water quantity control standard, and if not, then the project is not going to be compliant. So let's begin with taking a look at topography. Topography is important in identifying where the stormwater flows and is required to determine drainage areas and the time of concentration. Reviewers should be able to find the topography information on the plans and make sure that it's accurate. This, in some cases, may even require the reviewer to physically see the site as well. It's often difficult for us to find drainage maps in these stormwater reports. We also see situations where the drainage calculations in the reports do not match up with the drainage maps in the plans. We need to see existing and proposed contours. We need to see the point of analysis, time of concentration flow paths, and the drainage area to each point of analysis. The reviewer must be sure that the data used in the calculations matches the various maps and plans. This information must also be included on the drainage plans as well. It's very important to understand that each drainage area needs to be calculated separately. The reviewer should see the following calculated separately for each drainage area and must check the calculations for each drainage area. You should not assume that if one calculation is correct, then the rest are correct as well. So here is an example site. The flow was evaluated as sheet flow, directed primarily in a southerly direction. However, we received complaints of flooding along the road that is lying to the east of the project and from the area northwest of the project. It was determined that the drainage areas were not delineated correctly. Whether or not that was due to an incorrect evaluation of the topography, that's unknown. But this shows why it's important to properly evaluate the topography and delineate drainage areas. To prevent those issues from occurring, the reviewer must verify that all drainage areas are outlined correctly. The proper time of concentration flow path is used, and the time of concentration is calculated properly. The reviewer needs to make sure that any natural ponding on site is included in the model. This is often overlooked, and ignoring it for the existing condition means the allowed proposed volumes will be larger than they actually should be. So on the same example site that was shown before, there was a 6-inch deep ponded area within the shape that's depicted here. This was ignored, and the basin was made significantly larger than was needed. If there are any questions as to whether areas of ponding exist on site, and it cannot be determined from the photos of the site, you may just have to go there in person and see the actual site. The reviewer should be checking land cover next. Land cover should be clearly marked on the plans and be specific to what the land actually is. It should also include any existing BMPs that are on site as well. The reviewer must verify that the plans and cover descriptions in the report match what is actually on the site. Aerial photos can be used to make sure the most pervious cover that existed in the past 5 years has been used in the calculations. Again, it may be necessary for the reviewer to verify land cover conditions in person to make sure that they have been accurately described. Lisa has gone through how to determine soils, but just to reiterate, it is important to make an accurate determination of the soil types on site. The type of soil greatly affects the functionality of a BMP. So again, the reviewer can find soil info at the NRCS Web Soil Survey webpage at the link provided here on the slide. If information on these sites soils cannot be found, use the methods found in Chapter 12 to determine the hydrologic soil group, either from the default HSG method or from soil testing. Making sure that the soil data for the site is accurate is a critical part of the review process. Inaccurate soil information can make or break a stormwater BMP. So good practice generally is to review soil testing first. The rainfall depth and intensity information should come from these sources. You will need to make sure that the current precipitation adjustment and future precipitation change factors are appropriately applied for the 2-year, 10-year, and 100-year storm events using these tables on the slide, which are found in Chapter 5 of the BMP manual. NRCS has developed distributions for New Jersey, including NOAA C and D, which the BMP manual requires use of. These are already built into many stormwater modeling programs, such as HydroCAD. The reviewer should check that the correct distribution is selected, dependent upon where the site is located. The reviewer should next look at time of concentration. Information on how to calculate it can again be found in Chapter 5 of the BMP manual and the National Engineering Handbook. We also need to determine if the time of concentration in the pre-construction is appropriately calculated. We need to make sure that they are not underestimating this value. And we need to make sure that the Manning's sheet flow roughness coefficient is 0.4 or less for the time of concentration calculations. So just reiterating, according to the NRCS, the maximum Manning's roughness coefficient to be used is 0.8 for woods with dense underbrush. But in New Jersey, we do not have that situation, and the maximum Manning's coefficient for sheet flow in New Jersey that may be used is 0.4. Anthony covered this in Module 2, and more on this can be found in Chapter 5 of the BMP manual. As a reminder, again, you will need to use the current precipitation adjustment factor and future precipitation change factor tables found in Chapter 5 to calculate the travel times for current and projected storm events using the 2-year, 24-hour storm event, which will be used to calculate the P2 parameter. So look back through the handouts for the calculations presentation for Module 2 for more information on the correct way to calculate time of concentration. So in summary, the reviewer must make sure that the sheet flow, shallow concentrated flow, and channel flow inputs are all correct. They must make sure that the proper time of concentration was used with the corresponding method. They must check the pre-construction time of concentration calculations, and the reviewer must now check the post-construction time of concentration calculations, as it is no longer allowable to be assumed. Curve numbers are associated with the NRCS methodology and are used to calculate the amount of runoff caused by a specific amount of precipitation. The reviewer must be sure that the curve numbers correspond with each specific area based on land cover and hydrologic soil groups. The curve numbers are based on a presumption of good hydrologic condition unless the design engineer provides evidence showing different conditions. Again, this was covered in Module 2. Here's an example of what a land cover table might look like from an engineering report. You see here the land cover, the area of the cover, soil types, HSGs, and associated curve numbers. The reviewer must check these numbers and land cover types against what is shown on the plans. Sometimes you could see that they do not even match up. So always check to make sure they correspond to each other. So in all, the reviewer must check that curve numbers are justified in the report. You can verify these in the National Engineering Handbook. The reviewer is responsible for making sure the chosen values are reasonable and that they are accurate. Now I'm going to hand it off to Anthony Roblick, who will take you through the rest of stormwater runoff quantity control.
Okay, thanks, Manesh. Just bear with me a moment while I switch this over to my screen. Okay, all right. So, so now we'll continue with unit hydrographs. So we have the two types of hydrograph, the SCS hydrograph and the Delmarva hydrograph. When reviewing NRCS method calculations, the SCS unit hydrograph should only be used outside of the coastal plain area of the state, except in very rare cases where the design engineer can prove that the conditions that characterize use of the Delmarva hydrograph are in no way present on a site within the coastal plain, or use of the Delmarva hydrograph is not permitted, such as when sizing an MTD. Other than those cases, the SCS unit hydrograph should not be used within the coastal plain. And correspondingly, the Delmarva hydrograph should always be used for sites within the coastal plain area. And use of the Delmarva hydrograph is only acceptable within the coastal plain. But whichever hydrograph is being used, the reviewer must make sure that the same hydrograph is used for both the proposed and existing conditions. Okay, moving on to talk a little bit about runoff routing. So as you know, runoff from pervious and impervious areas is required to be routed separately. This is something that was required in our stormwater management rules. It's the reviewer's job to make sure that that this has occurred and that the areas are routed separately. And this can be verified by confirming that the modeling printouts provided do not show a composite curve number. If the reviewer sees that a weighted average of pervious and impervious areas was being used, they should note that as being incorrect. And please take note that Chapter 5 of our BMP manual has some examples and information if there's unconnected impervious area being proposed on site. And then this last point on this slide is if an off-site discharge point or a point of analysis receives runoff from several sub-drainage areas, then the peak flow rate at the discharge point cannot be a simple sum of the peak flow rates from each of the sub-drainage areas. The hydrographs from each sub-drainage area should be combined to find the peak flow rate at the discharge point. Okay, one situation that we often do not see correctly addressed is depression storage. The reviewer should identify if any depression storage areas exist on site and that they are included in the model. Depressions can provide stormwater management benefits and should be protected if possible. One problem that arises from ignoring depression storage in the pre-development condition is that it is not possible to accurately calculate time of concentration. So the reviewer must make sure that the depression storage is being modeled as an existing basin in existing conditions. So in general, this is the procedure to follow when reviewing existing condition depression storage somewhere within the confines of a proposed development. So the reviewer must make sure that the depression area is modeled. The time of concentration is calculated from the outlet of the depression to the point of interest correctly. Lag the depression outflow hydrograph by the calculated time of concentration, and then calculate the time of concentration for the remaining area of the site and route that separately. So this is the one example of depression storage that was shown earlier. Had this site been modeled accounting for the existing depression storage area, there most likely wouldn't be the issues that are there today. So when dealing with depression storage, the reviewer must review the time of concentration to the depression area, calculate the stage storage data for the depression area, model the outlet from the depression area, and route the contributory drainage area to the depression area. So now we'll take a look at an example of depression storage, and this happens to be modeled in HydroCAD. So the contributory drainage area, and that's here labeled as area EX2, is routed to the depression storage, and the reviewer can input the parameters into HydroCAD or another H&H modeling software to make sure that the depression area was calculated correctly. And so in this case, the depression is modeled as a small detention structure with 1,228 cubic feet of storage. And as you can see towards the bottom here, the storage discharges over a 22-foot-long broad-crested weir. And the lowest elevation of the storage is at 49.1 feet, and the highest surface elevation, and this is for the 10-year storm, is at 49.64 feet. And all this input information is taken from the site conditions. So after having reviewed all the input parameters, we should then review compliance with the stormwater runoff quantity standard. So option 1 is almost exclusively used for redevelopment. Chapter 5 of the B&P manual includes a discussion example illustrating this. As was mentioned back in Module 1, in order to meet option 1, the post-construction hydrograph cannot exceed at any point in time the pre-construction hydrograph. And that's for both the current and projected 210 and 100-year design storms. So here's an example where the post-construction hydrograph exceeds the pre-construction hydrograph. This example states that for a site located in Trenton, Mercer County, an approximately 2-acre paved parking lot is to be redeveloped as an office complex consisting of a new building, supporting parking area, and landscaping. And the existing lot has a slope of 1%, and the redeveloped site will be regraded to a slope of 5%. And it also states that the landscaped area will not receive runoff from the impervious surfaces, and that HSGC soils are present. So that in this example, we see that a proposed development is reducing the amount of impervious surface, but they're also increasing the slope of that surface. So a summary of the results from the modeling software is shown in the green table here on the right. And this is for the projected 100-year design storm event, so the largest storm event that we would model. And it looks like that the peak flow rate here and the runoff volume results for the post-construction condition are less than the pre-construction values. However, when we look into the comparison of the hydrographs, we can see that multiple values from the post-construction hydrograph actually exceed those from the pre-construction hydrograph at a similar time. And just to note that this is not the full hydrograph duration shown here, it's just a zoomed in portion just to make it easier to see where those points of exceedance are. So, although this site ended up reducing the amount of impervious coverage, and the peak flow rate of the post-construction hydrograph is less than the pre-construction hydrograph, the difference in site conditions from pre to post still resulted in this exceedance. And again, detailed information about this example is in our B&P manual, chapter 5. That's where this was taken from. Okay, so next we'll skip over option 2 since that was previously covered and go ahead on to option 3. So option 3 is the most commonly used, although that doesn't mean that errors don't occur in its use. Option 3 requires reduction of the post-construction peak flow rates to 50, 75, and 80% of the pre-construction peak flow rates for both the current and projected 210 and 100-year design storm events. This option requires use of green infrastructure stormwater BMPs that make use of a detention function and an outlet control structure to attenuate flow. So here's a list of the various Chapter 9 and 10 BMPs that can provide a detention function. So we see here BMPs such as pervious paving systems, small-scale bioretention systems, and infiltration basins. Note that the BMPs listed here are considered green infrastructure, which are required to be used to meet the stormwater runoff quantity control standard. Note that Chapter 11 BMPs, which are not listed here, would only be eligible to meet the stormwater runoff quantity requirement if a waiver or variance from NJAC 7:8-5.3 was granted, and 5.3 is the green infrastructure requirement. So as we mentioned earlier, the report shall provide routing calculations of all design storms for every sub-drainage area. The reviewer should check the inputs. So check that the pervious and impervious surfaces are separately calculated. Check that the correct NOAA rainfall distribution was used, either NOAA C or D. Check that the correct rainfall depth was input, whether from the NOAA precipitation frequency data server or the county rainfall data, and that the correct current precipitation adjustment factors or future precipitation change factors were applied. Also check that the time of concentration was properly calculated. And lastly, for this slide, check that the time span used captures the full storm event and discharge, and it isn't cut short. A lot of times we see the time span beginning at some time other than 0, or cut short when there's still a decent amount of volume left in the hydrograph. So we just want to see that the entire storm event and discharge is captured. So here's an example pond report. We'll take a look at this particular printout on the next slide. But on this type of printout, it's important to check if exfiltration was used in the routing and whether or not that is permissible, depending on the BMP used. Check that any orifice used is no smaller than the 2.5-inch minimum allowed diameter. And also this is where we would be able to check the BMP discharge rate for a given storm event and compare that with the maximum allowed for the post-construction condition. So this particular pond report is for the 100-year design storm, and the inflow area is a 1/4 acre of pervious surface. And on the printout, it shows that exfiltration was included in the routing calculation and is denoted here as discarded runoff, and that they use a 1.5 inch per hour exfiltration rate. Something else is to note that this BMP design does not infiltrate the entire 100-year storm into the subsoil. As you can see on the slide, primary here means the discharge of the 100-year storm through the outlet structure with a max discharge rate of 0.34 CFS. You will in most cases see a discharge in the post-construction condition. As it was mentioned in an earlier module, infiltration of the entire 210 or 100-year storm is allowed only when the existing site conditions are such that no runoff leaves the site for the pre-construction condition scenario, thereby constraining the design to infiltrate 100% of the volume produced by the post-construction condition for the same design storm. So in that case, the maximum storm that can be entirely infiltrated is the largest storm event with no runoff leaving the site in the pre-construction condition. Or the other case is if the volume of stormwater runoff to be fully infiltrated is required by a law or rule implemented by the Pinelands Commission, the Highlands Council, or any other stormwater review agency with jurisdiction over the project. If a proposed BMP is designed to infiltrate runoff into the subsoil, then the reviewer must check that a groundwater mounding analysis is provided. If there are infiltrating BMPs on site and no groundwater mounding analysis was submitted with the stormwater report, the reviewer shall ask that the design engineer shall provide it. There should be a groundwater mounding analysis provided for each proposed infiltrating BMP. Often, the groundwater mounding analysis will show the mounding as rising above the bottom of the BMP, which means that the runoff discarded through the basin bottom into the subsoil is reduced from what is assumed in the routing calculation. If this is the case, the routing calculation must be adjusted to use a smaller exfiltration rate, which will result in more flow being discharged through the outlet control structure. And if more flow is discharged from the outlet control structure, then you should check to see if the peak flow rate from the BMP is still below the maximum allowable peak flow rate. And if the discharge flow rate is above what's allowed, then the basin size or the outlet structure may need to be adjusted to provide more storage volume during the design storm. Okay, for green infrastructure BMPs, the detention component can be the detention of storage volume above the surface of the water quality design storm. For example, a small-scale infiltration basin that is designed to have an outlet orifice at the maximum water level elevation for the water quality design storm can have additional outlets at higher elevations for attenuating runoff from the current and projected 210 and 100-year design storms. Alternatively, you may design an under-drained bioretention system with storage pipes below the basin to provide the detention space for the current and projected 210 and 100-year design storms. Take note that provided storage space for detention should be located within the footprint of the basin. Designing a GI BMP with a detention component located somewhere downstream or otherwise outside the basin's footprint does not meet the design requirements stated in our BMP manual. Okay, now that we covered stormwater quantity, the next section the reviewer should check is going to be the stormwater runoff quality. So the stormwater runoff quality requirements are shown here. For new development, the proposed design must remove 80% of the total suspended solids in stormwater runoff generated from the water quality design storm from the net increase of motor vehicle surface. And also, although there is no numerical target, the reviewer must ensure the design removes nutrients to the maximum extent feasible. And the threshold for the water quality requirement is a 1/4 acre of net increase in motor vehicle or regulated motor vehicle surface. So each individual drainage area must meet the 80% requirement unless there is convergence prior to discharge from the site. Drainage areas discharging to different locations cannot be averaged together. And additionally, water discharging within a riparian zone must meet or must reduce TSS by 95%. Okay, regulated motor vehicle surface can mean more than just a brand new paved parking lot. It also includes pervious areas that are intended to be used by motor vehicles. Additionally, motor vehicle surface that is currently receiving water quality treatment by vegetation or soil, by an existing stormwater management measure, or by treatment at a wastewater treatment plant, where the water quality treatment will be modified or removed, is also considered regulated motor vehicle surface and will count towards that 1/4 acre trigger. Okay, just a quick note on pervious paving systems, since we are seeing them used more frequently under the current rules. The reviewer must make sure that pervious paving areas are treated as regulated motor vehicle surface when considering stormwater quality, so they count towards that 1/4 acre trigger. However, pervious paving systems designed in accordance with the BMP manual can assist in providing that required TSS removal. Okay, rooftop runoff. Rooftop or runoff generated by a rooftop is considered clean because it is not typically a significant source of TSS. However, it can be a significant source of nutrients, which the reviewer should make sure is considered in the design. And because of this, pretreatment of rooftop runoff may be a requirement depending on the BMP used, and the reviewer should consult the BMP manual for pretreatment information. So in the previous modules, we talked about the water quality design storm, which is unique to New Jersey. It's the storm that introduces TSS into our collection systems and waterways. It's nonlinear in its distribution and is fairly intense, with 1 1/4 inches of rain falling over a 2-hour period. And here's a graph depicting the total rainfall from the water quality design storm versus time. And you can find this graph in Chapter 5 of our BMP manual. You can also find this information tabulated in our stormwater management rules. Okay, so here's a list of the various Chapter 9 BMPs that can provide stormwater quality treatment. So these BMPs are considered green infrastructure, which is required to be used to meet the stormwater quality control standard. Note that Chapter 10 and 11 BMPs, which are not listed here, would only be eligible to meet the stormwater quality requirement if a waiver or variance from NJAC 7:8-5.3 was granted. And the BMP manual is designed to help the reviewer identify the design criteria that must be met for a proposed BMP to merit the approved TSS removal rate. So in addition to the TSS removal rates, there are phosphorus and nitrogen removal rates associated with almost every BMP in the manual. And this is a table identifying the different rates associated with the different BMPs. And this information is included in Chapter 4 of our BMP manual. And as you may have seen quickly in the previous table, but not every BMP is rated for 80% TSS removal. Sometimes a series of BMPs are needed to meet the 80% TSS removal requirement, or the more stringent 95% rate for projects discharging within a riparian zone. So when calculating the effective TSS removal rate from a series of BMPs, we use the equation in the third bullet point here, where A and B are the TSS removal rates from each of the individual BMPs. Okay, something else to note is that when a combination of BMPs are used, justification for the placement order is needed, and that is according to the hierarchy seen here. First considering TSS removal rate, then nutrient removal rate, and lastly considering ease of sediment and debris removal. Also, the reviewer should verify that two of the same kind of BMP are not used in series, as the downgradient one will not be as effective. And if we run through a quick example here of calculating the effective TSS removal rate for two BMPs in series, in this case, we have a vegetative filter strip, which by itself is rated for 60% TSS removal. And downstream of that, we have a small-scale infiltration basin, which is rated for 80% TSS removal. And if we put them in series, plugging in the values to the equation here, we get a combination or a combined effective TSS removal rate of 92%. Okay, nutrient removal. Nutrient removal is required for all major developments. As we saw a couple slides ago, some BMPs have adopted nutrient removal capabilities, but often the best way to handle nutrient removal is through source control. So BMPs being used to meet the water quality standard must be designed in accordance with the BMP manual. Alternative designs that deviate from the BMP manual requirements may be used, but these designs must be submitted to the department for approval. So in summary, when calculating a water quality review, the reviewer must, one, ensure that the BMPs used on site to meet the stormwater quality standard are from Table 5.1 or Chapter 9 of our BMP manual and are adequate to achieve the required TSS removal rate and designed in accordance with the BMP manual. Two, ensure that stormwater runoff that requires water quality treatment is being treated. And lastly, ensure that a deed notice of the stormwater BMPs used on site is submitted for approval and recorded in the county clerk's office prior to the start of construction. Okay, so now moving on to some more specific details about the different water quality BMPs. There are some general design criteria that applies to all water quality BMPs. So all BMPs must drain down in 72 hours. If the BMP is installed adjacent to pedestrian traffic, the drain time should actually be 24 hours. All infiltrating BMPs must have a minimum 2-foot separation from the seasonal high groundwater elevation, and under drain GI BMPs must have 1-foot separation. So here are some of the most commonly used water quality BMPs. Under the current rule, we've seen a significant increase in the use of small-scale bioretention systems, pervious paving systems, and GI MTDs in particular. So every BMP in the BMP manual has a summary page. So this is the page for small-scale infiltration basins. The paragraph at the top describes how the BMP functions to remove pollutants and lists a TSS removal rate. The table shown below the description lists whether a BMP can be used to meet each of the design and performance standards. So as mentioned previously in Module 1, the green leaf denotes if a particular BMP meets the definition of green infrastructure. And any design type that does not qualify for this will be noted here. If there is a TSS rating noted across from the gold % sign, that means that the BMP is rated for that TSS removal rate if all of the design criteria are met, including there being a maintenance plan. And notice that the title for this chapter is green, and there are different colors for the different chapters, with green being for Chapter 9, Green Infrastructure BMPs, blue being for Chapter 10 BMPs, and black being for Chapter 11 BMPs. This is just a visual aid to help in grouping the different BMPs in our BMP manual and which rule requirements they would be applicable to meet. So if we continue on with small-scale infiltration basins, they are a very common BMP for water quality treatment. Small-scale infiltration basins achieve the 80% TSS removal rate and may also be used to meet the stormwater quantity and groundwater recharge requirements. Under the current rules, only the volume generated by the water quality design storm may be infiltrated, unless specific cases allow for the infiltration of the larger storm events, as we previously talked about. That means there should be one or more orifices or weirs in an outlet control structure to discharge those larger storm events. And this type of basin also has additional design criteria in the chapter, which is critical to preventing basin impairment or failure. And a failed basin, a failed or impaired basin will require retrofit or major maintenance. So during your review for small-scale infiltration basins, also check that the minimum thickness of the appropriate sand is present, and check that the basin is not used as a stockpile location during construction. Make sure there is anti-compaction language on the plans. If they are using a subsurface infiltration basin, there is an 80% TSS pre-treatment requirement to keep in mind. Also make sure that the hydraulic conductivity testing was performed correctly and that the design rate used should be between ½ inch per hour and 10 inches per hour. So some things you should not see for small-scale infiltration basins. If they are designed for water quantity, they must have an outlet structure for the larger storm events. The reviewer should also not see any under drains or liners in the design, or any topsoil or vegetation in the landscape or planning plan. And there must be no standing water in the basin 72 hours after the precipitation stops. So here's an example of 2 infiltration basins. So the top one is functioning correctly. And as you can see in the bottom one has ponding at the inlet locations, and there's a lot of vegetation established. So this is a pretty big basin. So something to consider is how will compaction from vegetative maintenance impact the ability of the basin to infiltrate? And additionally, the vegetation that is breaking down in standing water forms a biofilm that can cover the sand layer and greatly reduce the basin's ability to infiltrate. And that's why the BMP manual does not allow for vegetative bottom for an infiltration basin. Okay, moving on to small-scale bioretention systems. So bioretention systems provide more variability to address the rule requirements and are also very commonly used. Shown here is the summary page for small-scale bioretention systems from Chapter 9 of our BMP manual. As you can see in the table, this BMP can be used to meet the stormwater runoff quantity, quality, and groundwater recharge rule requirements. Small-scale bioretention systems rely on healthy, dense vegetation. The type of vegetation and the thickness of the planting bed determine the TSS removal rate. And here's a table with some design parameters and the corresponding TSS removal rates. And this is taken straight from our BMP manual. So small-scale bioretention systems can be practical, a practical BMP to implement in urban areas. Rain gardens are a type of small-scale bioretention system and are encouraged under the new rules. There are even types with under drains to help facilitate drainage. And this is just an image of a small-scale bioretention basin implemented within an urban environment. Small-scale bioretention systems have specific requirements regarding the depth of the planting media and what that planting media consists of. This planting media is designed to support dense vegetation, but also convey stormwater. So the planting bed must be between 18 and 24 inches in depth, and the planting media has specific composition requirements. And take note here that the composition of inorganics is measured by volume, but the organics is measured by weight. Small-scale bioretention systems also have specific requirements in regard to stormwater quality, depth, bottom slope, and density of vegetation. And they can all be found in the BMP manual. And the reviewer must make sure that this criteria is met for any bioretention system that is being proposed. Okay, so we covered two examples, small-scale infiltration basins and small-scale bioretention systems. But in general, all BMPs that infiltrate runoff have specific design criteria associated with them, which can be found in the BMP manual. And reviewers should make sure that the criteria is being met. So to go over some of that common design criteria, reviewers must check that the soil permeability was tested and that a factor of 2 was applied to any tested permeability rate to get the design permeability rate. And infiltration BMPs may have design permeabilities between a ½ inch per hour up to a max of 10 inches per hour. Some other common criteria, BMPs designed to infiltrate must have 2 feet of separation from the seasonal high water table. When we get into the groundwater mounting analysis, which you can also read about in Chapter 13, you'll see that infiltrating stormwater causes a temporary and localized rise in the groundwater table. And if this rise is great enough, it can slow down the rate of infiltration so that the BMP does not drain within 72 hours. So this means the basin must be enlarged or retrofitted. And that's why it's so important to make sure that soil testing was done correctly and that the seasonal high water table is properly located. Okay, lastly, when reviewing BMPs designed to infiltrate, make sure that anti-compaction language is present along with post-construction soil testing. It would be helpful to include this drain down information also in the maintenance plan so that it can be easy to find in future during maintenance activities. So that's it for how to review a project 1. Thank you for your attention. And here's our contact information, both myself and Manesh. And I'm going to turn this back over now to our moderator.
I don't see any question that being posted on the chat that I haven't answered. So we will take a break, a 10 minutes break for now. So please come back at 2:38. Thank you. Good afternoon. My name is Chen Wu. I'm going to present how to review a project part 2. The goal of my presentation is to learn how to review BMP for compliance, and also I will address the MTD design, and then how to review the safety requirements, and also I will touch upon the groundwater recharge spreadsheet. So in module 1, you have learned that the BMP chapter are arranged in accordance with the order of BMPs listed in table 5-1, -2, and -3. So here are the chapter that's corresponding to those the BMPs. This is in the table, and each subchapter of chapter 9, 10, 11 has a section titled Design Criteria. So a BMP needs to be designed to comply with those design criteria in order to get the credit TSA removal rate. And here for the 10, for the table 5-2 and then 5-3. And a note for the BMP on table 5-3. This is BMP and not GIBMP. So you will need to get the waiver or variance before you can use it for meeting quality, quantity, or groundwater recharge requirements. So here are some highlights of the design criteria in some of the BMP chapter, but for the detail, please refer to the full chapter for details. For cistern, if you want to design a cistern, the storage volume need to be at least for the runoff from the WQDS, which is water quality design stone, but the cistern needs to be emptied by the reuse demand within 72 hours. For dry well, the design volume of dry well cannot exceed the runoff from the WQDS, but it can have the design volume that's smaller than the WQDS. And although a dry well cannot be used to treat runoff from motor vehicle service, it can prevent clean runoff from being commingled with the dirty runoff from the motor vehicle service, such as a driveway, and reduce the size of a BMP needed for the water quality treatment. For pervious paving system, if you want to design a pervious paving system, the storage volume need to be at least equal to the runoff from the WQDS. Although there's no surface runoff from a pervious paving system, need to be used 98, but you need to use serial number 98 in order to size the amount of the precipitation and the runoff falling from the pervious paving. The next one is the small-scale infiltration systems. Infiltration BMP means one designed to infiltrate runoff into subsoil. Therefore, if the designer called the BMP an infiltration BMP, it cannot be designed to have under drain system to direct runoff away from going down to the subsoil. Also, an infiltration basin cannot have vegetation on the bottom of the basin. If it has, it cannot be recognized as an infiltration basin. Small-scale sand filter. A small-scale sand filter system that is intended to meet the GI standard cannot be designed with the under drain. Then for the vegetative filter strip, not every piece of the vegetated area can be recognized as a vegetative filter strip. Only those vegetated areas that are designed and maintained strictly in compliance with the design criteria of the vegetated filter strip chapter can have the TSA removal rates. And the TSA removal rate and associated the length of the vegetative filter strip depends on the vegetation, soil type, and the hydrologic soil group and the slope. There are figures and curves that you can use to find the TSA removal rate associated with the vegetation soil type and hydraulic soil group and slope for vegetative field strip. So please check the BMP menu. And I would like to address the waypoint. There are two types of waypoints. First, one type of waypoint is the non-GI GI waypoint. Another one is a non-GI waypoint. And let's take a look of the details. So for the non-GI waypoints, can be used for water quantity and quality only when a waiver or variance from the stormwater management rule of the CO is obtained, and it needs a minimum of 0.285 acres permanent pool service area, and the minimum ratio of the permanent pool volume to the water quality design storm volume is 1:1. The minimum drainage area is 20 acres. Require very low permeability rate soil, our impermeable liner. For the waypoint, they can be recognized as a GIBMP. It can be used. It's allowed to be used for water quantity without any variance. But if you want, if that the GI waypoint is to be used for water quality only when a waiver or variance for the rules is obtained. So in addition to the design criteria for non-GI waypoint, GI waypoint needs to be maintained at least a 10-foot wide area, have the native vegetation, and at least 50% of the shoreline, and it needs to including a stormwater runoff retention component designed to capture stormwater runoff for beneficial use, such as irrigation. And volume available for the beneficial use should be equal or greater than 1.5 inches of the rainfall over the drainage area of the GI waypoint. Stormwater reuse demand is based on 3 days consecutive use. And beneficial reuse should not cause water level to lower than the permanent pool water level. And GIBMP that infiltrate WQDS runoff into subsoil cannot provide WQDS runoff to GI waypoint for beneficial use. So if you design, for example, if you design bioretention, small scale bioretention basin that upstream of the waypoint, a GI waypoint, the runoff being infiltrated through those bioretention BMP cannot count as the WQDS that into the downstream GI waypoint. And something about the landscaping irrigation. The beneficial use of the GI waypoint is often used in landscaping irrigation. The method to estimate the irrigation use should be based on some reasonable assumptions. You cannot readily assign a value like 1 inch per acre per day to calculate the irrigation use. And here's one reference. You may use it. NRCS has NJ New Jersey Irrigation Guide, which provides one method to estimate the irrigation needs. If you want to use another method, you need to provide a well-recognized publication showing the method and the variables that are used in your calculation. And we will work on the guidance and then for those situations. But for now, we will consider on a case-by-case basis if you want to use the beneficial use to calculate the water demand. And on the slide, we have those details for using the NJ irrigation guide. Please read it. So next topic is to address the safety requirements. First of all, trash rake and overflow grade are needed. So it's in the BMP menu, and we have the illustrations to show those requirements. Please take a look of those details. When you review a project on the site plan and the details drawings in the site plan sets, they should have those trash rate information for your review. Also, if there's a permanent pool, then it would need safety ledges. And the requirement of the safety ledges are shown on the slide, and it's also available in the rules. Please take a look. So next topic is the MTD. So under stormwater management rules effective on March 2nd, 2021, there are two major categories of the MTDs. One is GI MTD, one is a non-GI MTDs. A GI MTD should infiltrate runoff into the subsoil and or treat the stormwater runoff through filtration by vegetation or soil. An MTD that uses a biofiltration media and can be configured as above ground and incorporate the tree box, planter box, or shrubs will meet the GI definition. Any MTD with biofiltration media that would be placed below ground as a vault without any vegetation can be considered as a GI BMP only if the device infiltrates the stormwater into the subsoil. And also further, the below ground device will need to meet the NJDEP BMP menu conditions for the soil below the MTD. For example, there has to be needs to have the minimum infiltration, tested the infiltration rate of 1 inch per hour or greater, and have at least 2 feet of separation from a seasonal water table. Another category of MTD is the non-GI MTD, which do not infiltrate runoff into subsoil and or treat the stormwater runoff through filtration by vegetation or soil. Just a reminder that if the design proposed to incorporate MTDs to meet the water quality design and performance standard, then they must incorporate GI MTD into the design unless a waiver or variance from using non-GI MTD is granted. And we want to emphasize that the review engineer must read the certification letter before doing the review. The certification letter provides the calculation methods, sizing, and the configuration of the MTD. And the maximum treatment flow rate is calculated based on the peak flow rate and from impervious surface during the water quality design storm. And the certification letter also has other criteria conditions. For example, that one of the MTD certification letter states that the inlet to the MTD can only be a single inlet. I think Dr. McGee mentioned this in module 2. And if the site plan shows there are 2 inlets direct flow into the MTD is not designed in accordance with the certification letter and cannot receive a TS removal rate that's stated in the certification letter. And that is because only specific MTD models from the MTD manufacturer was tested. The manufacturer's other models not listed in the certification letter, even though they are same type, cannot be used to meet the water quality design and perform standards. And also the MTD were tested under specific configurations and installation specification. MTDs that deviate from the configuration or installation specification cannot be used to meet the water quality design and performance standard. For example, MTD has a drawing in the certification that shows only one inlet or that has a vegetation that had to meet those requirements. So if the sizing requirement in the configuration letter indicate that the sizing is based on the maximum treatment flow rate and also the maximum inflow impervious area. Then the model selection should be based on both the flow rate and the inflow impervious area, and whichever result in the highest minimum configuration should be the model being selected for the project. So again, for the GMTD, that the MTD is certified based on the treatment provided by vegetation. You will see the certification says that the minimum vegetation cover should be maintained at 85%. So if that the vegetation is lack of maintained or the vegetation was not being designed and installed as the certification later requires, then the MTD cannot be recognized as GMTD and cannot meet the water quality standard. And also, that's another emphasis of that. If the MTD says that the GIMTD must infiltrate the runoff into subsoil in order to qualify a GIMTD, then you cannot have the MTD that's being installed underground without infiltration of the runoff into the subsoil. And the calculation method for the MTD design is based on NRCS. So just a note that the rational method is no longer a valid method to be used to meet the stormwater management rules. And example 5-9 in chapter 5 of the BMP manual demonstrate the calculations. And for the NRCS method, only the SCS standard dimension that's unihydrograph can be used. And the precipitation depth is for the time. So for the calculation of the time of concentration under the current rule should be the projected 2-year storm. So you have to, I think we mentioned this, you have to apply the future precipitation change factor in table 5-6 of the rule and to the 2-year storm that you can find from NOAA's precipitation data and apply the factor in order to obtain the projected 2-year storm, and that is the storm to be used for the time of concentration. So here's one example. I think you can read yourself. Basically, is the 2-year storm, and it should be the projected 2-year storm. And then you use the time of concentration that based on the chapter 5, and then you calculate the WQDS peak flow rate, and then you compare that with the model that being listed in the certification letter, and you can find or you can verify if the correct MTD model being selected. So here is the continuation of the example. You can read it. As that here, you can see that the model M2 is the smallest model that has a maximum allowable drainage area that can greater than the 0.26 acres contributory drainage area. And then you check the WQDS. And so model 7 is the smallest model that can provide the maximum treatment flow rate equal or greater than 0.82 CFS. So between model 2 and model 7, the model 7 M7 should be the MTD model being selected for the project. So in summary, for the BMP design, BMP should be designed to meet the criteria in the BMP manual. And multiple BMP can be used in series when necessary, but you have in the chapter 4 of the BMP manual is there some limitation. Please check it out. So infiltration BMP requires the detailed soil permeability testing that's being emphasized, and we cannot say more anymore that the soil permeability rate testing is very important for the infiltration BMPs. And detention BMPs, which means the GI weight pounds, those kind of BMPs that provide the detention. You need to use the detention time to determine the TSA removal rate. If the GMTD being GI weight pounds has been obtained various to use it for the water quality, and MTD design using the MRCS method. So next topic is the groundwater recharge. And here's the rule requirements. It's the first one is to demonstrate through the hydrological and hydraulic analysis. The science is the stormwater management measure maintain 100% of the average annual pre-construction groundwater recharge volume on the site, or infiltrate the difference in the projected 2-year storm runoff volume. So let's take a look at the infiltration of the projected 2-year storm. Is easy. You do the water quantity calculation, you will know those values, and you can just easily to do the calculation and do the design. But in our experience, that it will result BMP that's greater than it needs. And if you infiltrate too much of the runoff into the subsoil, it may have the groundwater mounting issues. So here, as I said, that you can obtain those values from the quantity design, which is based on NRCS methods. But as you review it, you still need to have the design engineer to show the pre and post construction project 2-year storm, the difference of the volume. And you have to check whether they use the NRCS method, and also appropriate the curve number and time of concentration to match those quantity and quality analysis. So here example that there's NOAA rainfall depth. So you can see how we come up from the NOAA's depth and then to get the projected storm for the recharge volume. So after that, you can calculate based on the projected 2-year storm. You can obtain the post-construction and also the pre-construction runoff volume, and you can have the increase. And then another method is to maintain 100% of pre-development groundwater recharge. And this method needs to use the New Jersey groundwater recharge spreadsheets. And under this method, you need to review those inputs for the pre and post construction conditions. So here is a brief first page of the groundwater recharge spreadsheet. The orange shaded area are for the inputs, and the gray area are for the outputs. So on the first page, on the left are the inputs for the pre-construction condition, and the right are for the post-construction conditions. And we want to emphasize that the infiltration is not same as the groundwater recharge. Infiltration is only the process to allow the runoff into subsoil. For groundwater recharge, the runoff needs not only to drain into the subsoil, but it has to pass the root zones. And so for different soil, there are different depths of root zones. And so the soil in this spreadsheet play an important role in the calculation of annual recharge and the recharge provided by the BMP. So on the first page, you have to input the municipality and then cover and the type of soil. the soil series and also the acreage of those land covers. And it's important to know the municipality, choosing different municipality would determine the pre-construction conditions annual recharge. So please be careful to review if the municipality is where the project is located. And the output will be the annual recharge credit deficit from the post-construction condition. So when you review the spreadsheet, you need to review whether soil and the land cover match the site plan, whether the soil determined by soil survey or using the Chapter 12 defaults. And also the area must, for the pre and post construction must match. So it's often the question that in the input that when you find the soil from the web soil survey, some of the soil doesn't have the designation of the soil series, or it doesn't have the designation of the HSG. So here's a table in our chapter 12 that match the default soil series and the HSG designation. So if you cannot find the soil series or you cannot find the HSG, you can use the table to match and put the input into the spreadsheet. And for any soil that's being designated as the HSGD soil, you can find any soil series that result in zero annual recharge. And here, the second page for the recharge spreadsheet. And let's take a look. So here, the parameters for the annual recharge spreadsheet would bring over to this BMP design spreadsheet, which is the VDF. That's a post-development deficit recharge, and default from page 1 or other input. And AIMP means the post-construction impervious area that would contribute to the recharge calculation. And the annual BMP recharge volume will be calculated automatically by the spreadsheets. And on the second page, there's a parameter titled SEC BMP, which is the post-development site segment in which the proposed recharge BMP will be located. And if you put it at 0, it's use the average of the whole size land cover. But for the the design, when you review the stormwater management design, the BMP location should have been known. So it should not be 0. It should be where the lane segment where the BMP is going to be proposed. The parameter for the BMP has the area, which is the ABMP, and also the depth of the water in the BMP, which is DBMP. So for the BMP filled with stone, then the effective depth should be the actual depth times the porosity. So for the slope by return swell, then you should be able to use the ABMP times the DBMP to keep the same volume and to get the average of either the ABMP or the DBMP. Another factor that's confused the designer or the reviewer is the DBMPU. So it's the vertical distance from the vegetated ground surface to the maximum water level of the BMP. And we have the figure in the chapter. You can take a look. And so it's a positive if the maximum level is below the ground surface, or if it's negative, then it's the above the ground surface. And DXC is the vertical distance from the vegetated ground surface to the bottom of BMP. So for example, in this one, the water level is above the, there is vegetation in the bottom, so the dBMPU is negative. And the DXC, because the vegetation from the bottom to the vegetated ground is at the same level, so it's 0. And for this configuration, the vegetated, there's no vegetation in the bottom. This, for example, for the infiltration BMP. So the dBMPU is a positive value because the vegetation is above the water level. Then the depth to the DXC will be the difference from the ground level to the bottom of the BMP. And here's one example. For example, the pervious paving. So you will have the dBMPU is a positive value. We are assuming the vegetated ground surrounding the pervious paving is the vegetated ground, and so you measure that will be the positive value because it's above the water level. So, and for the DXC is the from the bottom of the impervious for the pervious paving systems bottom to the ground level. So here's one example that shows the water quality, water level, and the ground. And then this example is an infiltration BMP. So you can see that it has all of it at the elevation 13.36. So the configuration of this BMP is same as the one that has no vegetation in the bottom. So the dBMPU is the ground level and the water level as the first orifice. So it's a positive 1.64 feet, and dx is the difference from the ground level to the bottom of the infiltration basin. So we can calculate those parameters accordingly from the site plan. So because this one is a sloped BMP, so we have to calculate the BMP. So we can have the volume divided by the depth of the BMP. So we get the ABMP value. So if the same values, but if you change the condition, the BMP type from the infiltration basin to a bioretention basin, then the ABMP would be the same, dBMP would be same, but the dBMPU and the dx would be different. So that would make the calculation output differently. So for the recharge of stormwater BMP, there are some limitations. First of all, is that you cannot recharge the high pollutant loadings of industrial stormwater that exposed to the source material. So for some establishment with review, there are like the gas station, gas pump. So the runoff from the area should be directed away from the recharge BMP. And there are other BMP requirement, the design requirements. So you have to meet those design criteria that's addressed in chapters 9, 10, 11. And for the BMP that designed to infiltrate must consider the adverse hydraulic impact on the groundwater table, which means the groundwater mounting analysis. So my presentation covers quickly, briefly about the some highlights of BMP chapters, safety requirement, MTD design, and groundwater recharge. And those have the BMP menus address those in details. So please take a look before you review our design of BMPs. So here's my information. If you have any question, you are welcome to email me. So the next presentation will be the groundwater mounting analysis.
All right, hello everyone. I will share my screen for the groundwater mounting presentation. All right. So hello again, everyone. It's Peter Pliantos from the Municipal Stormwater Engineering Unit. And this presentation will dive into the groundwater mounting analysis requirements and calculations necessary for the use of infiltration BMPs. This material is covered in depth in Chapter 13 of the BMP Manual. My goal with this presentation is to cover the requirements under the stormwater management rules, as well as concepts, methods of calculation, and examples, all in relation to groundwater mounting analysis. The rules require we assess the hydraulic impact of the proposed development on the groundwater table and design the site to avoid adverse impacts. In order to describe what is an adverse impact, let's take a look at what happens when we infiltrate stormwater. Below the surface, the groundwater table rises locally, and then it needs some time to spread out before returning to stasis. When we force a concentrated amount into one area, we get mounding. This increase slows down the ability of the basin to infiltrate, so we can have problems if this increase is large enough to slow down the rate of infiltration beyond our 72-hour window, or from repeating the slowing down over and over, the basin can experience failure. Additionally, as this mounding spreads out, it can reach adjacent structures such as basements and septic systems. Let's take a look at a nice graphic that illustrates this. This illustration is in the paper prepared by Glenn Carlton from the United States Geological Society, or USGS. We have a house near an infiltration basin. The blue color area below everything is known as the saturated zone, whose top surface is the seasonal high water table. Imagine, if you will, that it rained. The rain has now stopped and runoff has collected in the basin. As stormwater infiltrates below the bottom of the basin, we get a temporary localized increase, or mounding, below the basin that is caused by stormwater infiltrating into the subsoils after the storm event. In order to dissipate, the volume of water under the curve has to move outward and downward until it returns to how it was before the rain. We need to calculate the maximum height of the mounding in order to assess the impact of infiltrating stormwater on the basin and on nearby structures. One method of calculating the height of groundwater mounding is covered in Chapter 13. That method, known as the Hantos equation, dates back to 1967. It requires the computing capabilities such as that found in the Excel spreadsheet developed by the USGS. You basically enter in certain parameters and then click the Calculate button to see the results plotted. Additionally, the user gets results in the cells of a spreadsheet. Now, there are certain ground rules, pun intended, for using the spreadsheet, so we'll go over what parameters we need to define, and then we'll look at making sense of the plot the spreadsheet creates by virtue of a macro. This is a screenshot of the Hantos spreadsheet. If you have used the spreadsheet in the past, you may find the spreadsheet a little bit different from the spreadsheet that was posted on the USGS website. That's because in March 2020, DEP published and adopted a new BMP manual chapter titled Chapter 13, Groundwater Table Hydraulic Impact Assessments for Infiltration BMPs, which provides both detailed guidance regarding the input values and examples illustrating how to conduct the groundwater mounding analysis. With permission from the USGS, we modified the spreadsheet. Here is how it looks today. All of the calculation algorithms are the same, but the units and the notes on the use of the inputs are modified to be consistent with other chapters of the BMP manual. Chapter 13 and this spreadsheet are available at the link shown on this slide. To get more familiar with the hand-touch spreadsheet, let's define the parameters listed here and establish the assumptions for their use in the spreadsheet. The first input parameter is the recharge rate. In the spreadsheet, you must use the design value for the vertical saturated soil hydraulic conductivity, which is 1/2 of the tested value of the vertical saturated soil hydraulic conductivity from soil testing performed in accordance with Chapter 12 of the BMP manual. The second input is the horizontal hydraulic conductivity, which is rarely tested on the scale of a single site just for the purpose of conducting a groundwater mounding analysis. Therefore, you will need to use presumptive values based on the site's location. If the site is located in the coastal plain, then the horizontal saturated soil hydraulic conductivity is presumed to be 5 times the recharge rate, i.e. the vertical saturated soil hydraulic conductivity. If the site is located outside the coastal plain, the horizontal saturated soil hydraulic conductivity is presumed to be the same as the recharge rate, that is, the vertical saturated soil hydraulic conductivity. If you recall, Lisa provided us in Module 2 with the link to the Bureau of GIS website where you can determine if your site is in the coastal plain. That link is also found on this slide. The next parameter is the specific yield, which is the volume of water that will drain from a soil specimen due to gravity divided by the total volume of the soil specimen. Coarse soil will likely have a higher specific yield than fine-grained soil, having the same porosity. Specific yield governs how much water the unsaturated zone can store when recharge reaches the water table. The more water that can be stored in the unsaturated zone, the lower the resulting mounding. Therefore, a soil having a higher specific yield may result in a lower mounding height than a soil having a lower specific yield, when other inputs remain the same. For groundwater mounding purposes, specific yield is not calculated by subtracting field capacity from porosity. The hand-touch spreadsheet assumes that the BMP is rectangular in shape and the sides of the BMP are vertical. So we use the width and length of the bottom area of the BMP, also called the footprint, but since the mounding is highest at the center of the BMP, for graphing purposes, we use 1/2 of each dimension as the inputs for the length and width, which correspond to the X and Y axes, respectively, as the inputs. Now for BMPs that are not rectangular in shape, we have some additional guidance. For circular shaped BMPs, you want to use the radius of the circular basin as both X and Y. For irregular shaped BMPs, convert the shape to a rectangular shape that has the same depth of stormwater runoff to be infiltrated and is best fitted to the original shape. And then if a BMP is designed with sloped sides, you want to use the bottom footprint as the length and width of the BMP and use the total volume of the runoff to be infiltrated divided by the area of the bottom footprint to calculate the duration of infiltration period. And we will define duration of infiltration period in 2 slides, so bear with me. For the initial thickness of the saturated zone, unless proven by a field test showing the thickness of saturated zone beneath the proposed BMP, the default value is 10 feet. Note that the thickness of the saturated zone used in the hand-touch spreadsheet is not the thickness of a large regional aquifer. It is the distance from the seasonal high water table to the first hydraulically restrictive layer. If a value greater than 10 feet is used, it must be accompanied by on-site testing results that demonstrates the value used is appropriate. The input value must never exceed 75 feet, which is based on the preliminary results of research conducted by the USGS. The exact maximum allowed value may be subject to revision based on the final results of the research. Any on-site boring used to justify a value greater than 10 feet must be a continuous sampling boring for the entire drilled depth. The duration of infiltration period, T, is equal to the time required for the BMP to drain the volume of stormwater runoff at the specified recharge rate, and is equal to the volume of runoff to be infiltrated divided by the product of the infiltration area and the recharge rate, where the volume of runoff to be infiltrated may be either the runoff volume produced by the water quality design storm or the volume of runoff to be discharged through exfiltration, if exfiltration of runoff during basing routing is used. The maximum duration of infiltration period that may be used in the hand-touch spreadsheet is 72 hours. When hydraulically restrictive soil layers are present below a proposed BMP, one solution may be soil replacement. Let's analyze how that may impact the input parameters. In the situation where the soil is replaced all the way down to the seasonal high water table, there are a couple of things to note. The recharge rate shall be 1/2 of the tested vertical hydraulic conductivity of the soil replacement media, up to a maximum of 10 inches per hour. However, the horizontal hydraulic conductivity shall be calculated based on the original soil, since the original soil will be surrounding the BMP outside of the soil replacement. The low permeability soil will still be present in the surrounding area, and the resulting horizontal hydraulic conductivity will still limit the ability of the runoff to be dissipated into the saturated zone and may result in high groundwater mounding in the unsaturated zone. Therefore, the use of soil replacement in basin designs must still be carefully evaluated with a groundwater mounding analysis. Example 7 in Chapter 13 of the BMP manual describes a groundwater mounding analysis scenario where soil is replaced down to the seasonal high water table below an infiltration BMP. It is important to note if a shallower depth of native soils is to be replaced, rather than replacing soil down to the seasonal high water table, the recharge rate shall be 1/2 of the lowest vertical saturated hydraulic conductivity of the remaining native soil. Continuing on, there are some important relationships between maximum mounding height and the input parameters to note. Delta H max is the maximum height of the mounding, and the value calculated by the hand-touch spreadsheet is that which occurs at the end of the duration of infiltration period. This is explained on page 17 of Chapter 13. However, the hand-touch spreadsheet does not further calculate the mounding as it spreads out over time. We'll talk about this further in just a moment. A lower mounding height will happen when horizontal hydraulic conductivity increases, specific yield increases, or the initial thickness of the saturated zone increases. You cannot just use the results from the spreadsheet as it appears. The results have to be checked against the physical constraints of the design. If you get a resulting mounding height that is higher than the distance between the basin bottom and the seasonal high water table, you do not get an artesian condition. It means the recharge rate is adversely impacted by a reduced hydraulic gradient and will be slower. That means you'll have to run the spreadsheet again after you make some changes. Because there is a proportionality between the recharge rate and the duration of infiltration, as shown in this equation, the changes include using a smaller recharge rate and a correspondingly longer duration of infiltration for the same infiltration area and the same volume of runoff to be infiltrated. Furthermore, if the mounding height just touches the bottom of the BMP, the rate of recharge will also be slower than the design value for the vertical saturated soil hydraulic conductivity. When this happens, you can stretch the duration of infiltration period while decreasing the recharge rate, or you can spread the volume of runoff to be infiltrated over a larger area. When opting to increase the footprint, you'll be able to use a shallower depth. There are some limitations associated with how the hand-touch spreadsheet operates. The graph produced by the spreadsheet is comparable to a snapshot in time of the mounding that occurs at the end of the duration of infiltration period. Since it's a snapshot, it does not depict what happens over time as the mounding height decays and spreads out. During decay, while the maximum mounding height under the center of the basin will reduce, the mounding will expand into the horizontal direction and potentially cause the tails of the mounding curve to rise higher than the height at the beginning of the decay. This means that if an underground structure appears to be above the mounding predicted by the spreadsheet, or out of range of the mounding altogether, it may still be inundated when the mounding height decays, since the hand-touch spreadsheet does not provide the height of the tails of the mounding during the decay period. Therefore, caution should be used when applying the spreadsheet to analyze adverse impacts to subsurface structures in proximity to an infiltration BMP. Now that we better understand the inputs to the hand-touch spreadsheet and the results it provides, let's go on to some examples that illustrate the method and what to do with the results. The examples presented today are two of the ones included in Chapter 13 and are arranged from simplest to more complex. After a straightforward example, we will look at an analysis that shows infiltration will be at a slower rate than the design saturated soil hydraulic conductivity and what changes need to be made because we encounter an impact. In other words, we will see two different scenarios. For the first example, a major development located in the coastal plain proposes an infiltration basin whose bottom footprint measures 50 feet by 50 feet to infiltrate 5,000 cubic feet of runoff generated by the water quality design storm. And a couple other notes. The maximum depth of ponding water is designed to be 2 feet. Soil testing was performed in accordance with Chapter 12. The soil testing report shows that the seasonal high water table is 7.5 feet below the 6-inch thick bottom sand layer of the basin. The tested soil permeability rate of the most restrictive soil horizon below the basin is 4 inches per hour, and no nearby underground structures are present. All right, so let's start with some basic calculations. Typically, the soil testing provides results in inches per hour, so the value for T would also use hours as the unit of measure. For the duration of infiltration period, we divide the volume of runoff to be infiltrated by the product of the infiltration area and the recharge rate. Also, remember that the recharge rate is 1/2 of the slowest tested saturated soil hydraulic conductivity rate from soil testing. Therefore, the duration of infiltration period is calculated to be 12 hours. When using the hand-touch spreadsheet, it is helpful to make a table of the inputs and the results, so they are ready to be added in later to the report. These inputs are organized to follow the order they appear in the hand-touch spreadsheet. The recharge rate is the first parameter entered into the hand-touch spreadsheet, but it needs to be converted to feet per day if you are using the older version. Feet per day is just inches per hour times 2. So here we would use 4 feet per day for R. The specific yield is set equal to the default value of 0.15. The horizontal hydraulic conductivity is equal to 5 times the recharge rate since the infiltration basin is located in the coastal plain. The basin measures 50 feet by 50 feet, so we would just input half of each of those dimensions since the analysis is performed at the center of the basin. And the duration of infiltration period is obtained from step 1. We also need to divide hours by 24 to get the number of days, which is 0.5 for this example if we're using the older spreadsheet. T is less than the upper limit of 3 days. And the initial thickness of the saturated zone uses the default value of 10 feet. Alternatively, you can grab screenshots from the input section of the hand-touch spreadsheet, shown here with the parameter values from the previous slide entered in the gold shaded cells. This version of the spreadsheet is one that allows time to be input in hours rather than days and recharge in inches per hour. With the inputs entered, I clicked the dark blue Recalculate Now button and took the screenshot after the macro finished plotting the blue curve. The results show in the red cell in row 16 the maximum height of groundwater mounding, represented by the variable delta H max, equals 6.07 feet, which I have circled in light blue. And this is what will occur at the end of the duration of infiltration period. To put this into proper context, I've also superimposed a symbol representing 1/2 of the bottom of the basin. Since the seasonal high water table, which the spreadsheet always sets at y equals 0, is 7.5 feet below the bottom of the sand layer, the temporarily elevated groundwater table, located at y equals 6.07 feet at the center of the basin, where x equals 0, will not reach the bottom of the sand layer. Therefore, the assessment shows no adverse hydraulic impact to the proposed infiltration BMP from the groundwater mounding. Remember that had the height of the mounding been high enough to intersect the bottom of the basin, it would mean the mounding will interfere with the infiltration capability of the basin. We would have to run a new model or trial that would involve increasing the basin footprint to spread out the volume of stormwater being infiltrated. That will result in a lower depth of stormwater runoff in the basin since the volume is the same, and the duration of infiltration period would have to be recalculated before the spreadsheet is run again with these new parameter values. If you recall the duration of infiltration period equation from slide 21, the footprint area is in the denominator, so we would see the duration of infiltration period decrease proportionally as the area increases. Next, let's talk about when things go wrong, meaning adverse impacts. This slide is not for the example I just presented. It is meant to show you what happens in the spreadsheet when the groundwater mounding height is too high. If you click on the dark blue Recalculate Now button, and the results show delta H max in the area I have circled is larger than the distance from the seasonal high water table to the bottom of your BMP, you won't be able to tell just by looking at the graph. In this case, the seasonal high water table is 8 feet below the bottom of a basin that is 90 feet in length. The height of the mounding is calculated to be 9.51 feet. The plot by itself looks normal, but is it? We have to understand what is being plotted and check it against the reality of our design. The depth to the seasonal high water table is 8 feet. This does not mean groundwater will rise up in real life above the basin bottom like this. It means the temporary elevation in the groundwater table, located at the center line and above the seasonal high water table, will intersect and exceed the elevation of the bottom of the sand layer, meaning it interferes with the infiltration capability and therefore it will take the BMP longer to drain. Adjustment of the basin design is therefore needed to reduce the impact of groundwater mounding. So we have to adjust our parameters and run the spreadsheet calculation again. To do that, we have to reduce the value for R. We don't know exactly how much it will slow, but my first attempt will try reducing it by 50%. However, we are not ready to click Recalculate. The horizontal hydraulic conductivity is not adjusted since it is not affected by the reduced hydraulic gradient in the vertical direction. However, the duration of infiltration period must be proportionally adjusted to reflect this slowing down. For example, we would double the initial value for T if we halved R. Although we don't know the exact rate to which the rate would slow, even if it is slowed by 1/2, we're going to check the mounding for a value of T that is within the maximum allowable time period. Sometimes we call this stretching the infiltration period. Next, we recalculate and check the result to see if delta H max is now less than the distance between the seasonal high water table and the bottom of the BMP. You might try this one more time with the T a bit longer as long as the R value is proportionally reduced. If that doesn't work, you're going to check Chapter 13 for an example of changing the dimensions of the infiltration area. With that explained, let's move on to our second example. We're going to look at a drywall for the example of an adverse impact. Even a small BMP can cause one. A site is located outside the coastal plain. A 7-foot high by 5-foot diameter drywall is proposed to store and infiltrate 137.4 cubic feet of roof runoff from a single-family home for the water quality design storm. The house has a basement floor located just above the groundwater table. The edge of the drywall is 10 feet away from the house. Soil testing was performed in accordance with Chapter 12. The soil testing report shows that the seasonal high water table is 2 feet below the bottom of the drywall. The tested soil permeability rate of the most restrictive soil horizon below the basin is 4 inches per hour. And the drywall is circular, so we calculate its area to be 19.6 square feet and input it into the equation to calculate the duration of infiltration period to be 42 hours. Using the same type of chart, here are the values for our input parameters. 1/2 of the slowest tested saturated soil hydraulic conductivity rate is used for the recharge rate in the spreadsheet. The specific yield is the default value of 0.15. The horizontal hydraulic conductivity is the same as the recharge rate since the site is located outside the coastal plain. The duration of infiltration period is 42 hours, and the initial thickness of the saturated zone uses the default value of 10 feet. The results show the maximum height of groundwater mounding, 1.11 feet, that will occur at the end of the duration of infiltration period at the center of the dry well. The temporary groundwater mounding does not encroach upon the bottom of the dry well, where it would have impaired infiltration had the mounding extended that high. Are we done? No. The rules require we also check the impact to the adjacent structure. Recall that the vertical axis is situated at the center line of the dry well, and the groundwater mounding curve is symmetrical on both sides of the vertical axis. The basement is 10 feet away from the edge of the dry well, which is 12.5 feet to the left of the center of the dry well. The spreadsheet results indicate the water table is also temporarily raised approximately 0.4 feet at the basement wall location nearest the dry well, which is an adverse impact prohibited by the rules. Therefore, the dry well may need to be moved farther from the building to avoid the adverse impact caused by the proposed infiltration. Per the USGS paper, an increase of 0.25 feet or less is an acceptable depth for underground structures to be temporarily affected by groundwater mounding. The mounding height at 20 feet from the dry well is just less than that. But considering the limitations from the Hanto spreadsheet I brought up earlier, it would be advised to place the dry well even farther than 20 feet from the basement, since the mounding decay, which is not modeled, may result in a rising of the groundwater level at the basement area higher than as it is shown in the Hanto spreadsheet. This example shows that even a small infiltration BMP may have an adverse impact on nearby underground structures. If you haven't read it, Chapter 13 includes a lot more examples. Please see Example 7 in the chapter for guidance when replacing soil below an infiltration BMP. Also, Chapter 5 includes examples with groundwater mounding analyses and including exfiltration in the routings, which is allowed in certain circumstances for the green infrastructure BMPs. All right, so thanks everyone for your attention. Here's my contact info, and we are going to move on to quiz 3. So please stand by while I hand control to Manesh to administer the quiz. Thank you.
All right, thanks, Peter. It is time for quiz 3. I think you all know how this works by now, so I'll move through these first few slides fairly quickly. As I'm sure you remember, using a new tab or window, you will have the option to follow the link shown at the top of this slide, which will take you to the training website, where you will find the quiz links at the bottom. You will also find the link for quiz 3 at the bottom of this slide here, which staff will be pasting into the chat right now. Or you may use the camera app on a smartphone to scan the QR code found at the bottom right of the slide. Do note the quiz link and QR code will be posted in the chat by our staff very soon, probably right now. Once you click on the link for quiz 3, you'll be directed to the quiz, which is now open on SurveyMonkey. Do remember to make sure to click submit at the end of the quiz to get credit for completing it. You must answer every question before you can advance to the next screen and finally submit. And just a reminder, you may only take the quiz once. So here's everything all in one place. Just a reminder, the quiz link is also in the body of the email that was sent for the invite to this module. It is now 3:42, so take about 10 minutes and we'll come back at 3:52 to do the quiz review. Thank you. All right, hello everyone. We will get started with the quiz review right now. Due to time constraints, we're going to try and start at 3:50. So let's get underway. We're going to start with question number 4. Which one of the following is not a green infrastructure BMP? And the answer to this is D, the extended detention basin. These type of BMPs are found in Chapter 11 of the BMP manual and are not considered to be GI. Small-scale bioretention basins, vegetative filter strips, and pervious paving systems are all green infrastructure BMPs, and they're all found in Chapter 9 and Table 5-1 of the BMP manual. Question 5, when reviewing water quantity calculations, which of the following must the reviewer check for accuracy? And the correct answer is D, all of the above. There are various things you need to check, and land covers, basin designs, and hydrographs must all be checked for accuracy in a site review for water quantity. Question 6, which of the following conditions must be met when a stormwater BMP is allowed to infiltrate the entire runoff from the 2, 10, or 100-year storms? And the answer is D, all of the above. Infiltration of the entire 2, 10, or 100-year storm events is allowed only when existing site conditions are such that no runoff leaves the site for the pre-construction condition scenario, thereby constraining the design to infiltrate 100% of the volume produced by the post-construction condition for the same design storm. The maximum storm that can be entirely infiltrated is the largest storm event with no runoff leaving the site in the pre-construction condition. So for example, if there's no runoff for the pre-construction 10-year storm, but there is for the 100-year storm, then for the proposed condition, the maximum design storm that can be fully infiltrated is the 10-year storm. And the answers for B and C paraphrase what is found in the rules. Only small-scale GI BMPs can be used to infiltrate runoff of a storm larger than the water quality design storm, unless required by another rule or agency. And soil testing of saturated hydraulic conductivity must be performed strictly following Chapter 12 of the BMP manual. Question 7, what is required as part of the municipal stormwater management plan to grant variances or exemptions from the design and performance standards? And the correct answer is C, a mitigation plan. A municipality must have an approved mitigation plan as part of its municipal stormwater management plan to grant variances or exemptions from the design and performance standards. We will revisit variances though in Module 4, so just keep this in mind. Question 8, if you have an impervious surface that has existed for 10 years, but have removed this impervious surface prior to the submission of the application that includes a stormwater management review component, can you still use this impervious surface as an existing condition in the stormwater management calculations? And the answer here is B, no. We use the land cover that has the lowest runoff potential that existed on site in the past 5 years for the existing condition. If you remove impervious cover, anything you replaced it with is going to have a lower curve number, regardless of when that impervious cover has removed. So impervious surfaces removed prior to the application cannot be counted as an existing condition. Question 9, true or false? If a project has been reviewed by the NJDEP Division of Watershed Protection and Restoration, formerly known as dealer or land use, the municipality does not have to review it for compliance with its Stormwater Control Ordinance or RSIS. And the answer here is B, false. The municipality is required to review all projects that trigger their definition of major development, regardless of whether they were reviewed by the NJDEP Division of Watershed Protection and Restoration or any other regulatory agency. Remember, the municipality may have a slight difference in its definition of major development, and it can even be more strict than the definition in the stormwater management rules. Question 10, which of the following would be exempt from the groundwater recharge standard? And the answer here is B, a previously developed portions of a site in a designated center. So just being in planning area 1 is not an allowed exemption from the groundwater recharge standard, nor is redevelopment automatically exempt. Only previously developed portions of sites in the designated locations listed on the slide here can be exempt. Question 11, true or false? Reducing impervious surface on a redevelopment project always meets the water quantity control standard. And the answer is false. Reducing impervious surface can help meet the quantity standard, but you still need to meet and be compliant with one of the 3 water quantity options. So you'd still have to demonstrate you meet this standard. Question 12, can an infiltration basin be designed with a perforated under-drain pipe as a means of discharging runoff from the basin? And the answer here is B, no. An infiltration BMP cannot have an under-drain pipe if it wants to meet the criteria for an infiltration basin in the BMP manual. Question 13, true or false? The TSS removal rate requirement must be met on each subdrainage area of a site unless the discharge from each drainage area converges to a single discharge point on site. And the answer is A, true. You have to meet the standards for each drainage area, but also be aware that if runoff from drainage areas converge on site and no adverse environmental impact would occur as a result of compliance with any one or more of the individual standards, being determined utilizing a weighted average of the results achieved for that individual standard across the affected drainage areas. Question 14, when can a wet pond be considered to be a green infrastructure BMP? And the answer here is C, both statements above must be met. So in accordance with note D to tables 5.1, 5.2, and 5.3, only a wet pond designed to maintain at least a 10-foot wide area of native vegetation along at least 50% of the shoreline and include a stormwater runoff retention component designed to capture stormwater runoff for beneficial reuses, such as irrigation, can be considered a GI BMP in Table 5-2. Question 15, true or false? When the groundwater mounding reaches the bottom of the BMP designed to infiltrate, the infiltration into the subsoil would be adversely impacted. And the answer here is A, true. Yes, when the mounding reaches the bottom of an infiltrating BMP, the hydraulic gradient is going to be reduced significantly, and the flow rate infiltrated through the BMP is going to be reduced as well. And question 16, what method is used to calculate the groundwater mounding height? And the answer here is B, the Hantosh spreadsheet. This spreadsheet, which you can find on our website with chapter 13, will calculate the maximum height of the groundwater mounding directly below the basin. So that's it for our quiz review. We do not have time to go through the common design issues presentation, but the handout of this presentation will be provided for your own personal review. So that's the end of Module 3. Module 4, our final module in this session, is this coming Thursday, October 24th at 1 p.m. As always, thank you for your attendance and participation. Before we end, though, Changi and Lisa, are there any last-minute questions that need to be addressed?
I will answer the question in the chat. So if you have submit and complete the answers to the quiz, you may leave the meeting now. Thank you for your participation. Thank you.